Hello, everyone, and thanks for having me at this wonderful conference. I'm Sam Ponnada. I'm a finishing year PhD candidate at Caltech, working with Phil Hopkins and several others on topics related to the non-thermal physics of galaxies. And so just a quick disclaimer, I was thinking a lot about specifically the warm-hot CGM and X-ray observations when I wrote the abstract, but I'll be talking more about multi-phase CGM in general and a variety of synthetic observations today. So to preface, magnetic field and cosmic rays, the non-thermal components of galaxies, are very important. They've long been known to be a substantial source of pressure support in both the interstellar and circumgalactic medium, and potentially are important for facilitating thermal instabilities in the CGM as well, depending on who you ask. And perhaps most importantly, they're the railroads on which cosmic rays travel, and they determine the transport of cosmic rays throughout the ISM and into the circumgalactic medium, with cosmic rays streaming along magnetic field lines and also fluctuating or scattering off of fluctuations in the magnetic field on gyroresonant scales, which for the GeV-ish protons that we care about are something like 0.1 to 1 AU, so much smaller than any resolved scales in most observations or simulations for that matter. And their effective transport speed is often quoted as some effective diffusion coefficient that marginalizes over this streaming and diffusion speed throughout the ISM and CGM. And in the last decade or so, we were finally able to model the physics of magnetic fields and cosmic rays in the full multi-phase context of a cosmological galaxy formation simulation. And so this is a movie showing the formation of a Milky Way-like galaxy from the FIRE simulation suite, which I'll be talking a bit about today. And these are simulations that are cosmological zoom-in simulations of galaxies run with explicit treatments of star formation and feedback. And crucially, for the type of work I'll be describing today, most recently include ideal MHD and cosmic rays as well. And so groups, including ours, but several others, have in the past decade found that cosmic rays can potentially have very significant effects on galaxy formation if they can escape the disk with minimal losses and get into the halo, where they can establish these large cosmic ray pressure-dominated halos. And so what you're seeing here is a temperature slice of a same Milky Way-like galaxy from FIRE run without cosmic rays on top and with cosmic rays on the bottom. And typically with cosmic rays, the outflow structure is much more stable and coherent. This prevents cold gas infall from falling onto the disk and creating more stars. And so the runs with cosmic rays are typically a factor of 2 or 3 less in stellar mass due to reduced star formation at late times, whereas runs without cosmic rays are much more chaotic in their outflow structure and have warmer and more diffuse halo gas relative to the cooler and denser structure of cosmic ray-dominated halos. And of course, crucially for making realistic predictions of cosmic rays transported through the ISM and into the CGM, we have to have realistic magnetic fields, as this diffusion process occurs anisotropically. And so we've shown in a paper that FIRE simulations produce realistic magnetic field strengths and geometries in both the warm ionized phases of the ISM, the cold neutral phases of the ISM, and are in agreement with the very not constraining, but existing upper limits that we have from fast radio bursts piercing the intervening halos of L-star-ish galaxies in the hot ionized CGM. And in this work, we also looked at some potential effects that this extended cosmic ray-dominated halo and its subsequent effects on the gas distribution in the CGM can have on the dispersion measure as traced from fast radio bursts from extragalactic sources. And so what we're seeing here is the same Milky Way-like galaxy run without cosmic rays, with cosmic rays. Because of the cooler and denser halo structure in the cosmic ray-dominated runs, these typically have a substantially larger contribution of the dispersion measure coming from the CGM. And so a question that we want to ask is if we can look inside out, so placing an observer in the solar circle of the disk of one of these galaxies, maybe we can compare to some recent dispersion measure estimates that we have from X-ray absorption, where we have plenty of quasar sightlines probing the Milky Way halo. Hopefully in 10 years we have 10 million FRB detections that we can do the same exercise with. But for now, we can try to probe the structure of the warm-hot phase of the CGM through these mock X-ray DM predictions and compare to what we know from X-ray absorption data. And so this is work with Sanskriti that's in preliminary work. But what we're seeing is that despite the total DM perhaps being increased in these cosmic ray dominated halos, because the halo structure is much cooler and denser, there's very little hot gas. And so the hot gas DMs are much lower than what we infer from these X-ray DM measurements for the Milky Way. However, the higher order structure functions of the turbulence seem to be better in agreement. Confusing? Yeah, we'll see if we figure out something out with this. But crucially, all the works that I've mentioned before are using these simple assumptions of a constant in space and time diffusion coefficient for cosmic rays. This is because it's really hard to measure anything about magnetic fields in cosmic rays and galaxies. The only place we've directly measured a magnetic field strength and the cosmic ray energy density is in the solar circle of the Milky Way just outside the heliopause. And so every tracer that we have is very indirect. One of these common indirect tracers is synchrotron emission. Quick refresher of radiative processes. Synchrotron emission is something like the dirty convolution of the magnetic and cosmic ray electron energy densities integrated along your line of sight. So you have to make a bunch of assumptions to infer anything about one or the other. And so one of the most common sets of assumptions is the so-called synchrotron equipartition model. And imagine you're looking at a galaxy edge-on. In this model, it's assumed that this emitting region is some uniform gas of 1 to 2 kiloparsecs, which should immediately raise alarm bells given the name of this conference. But in this model, you have to assume there's some homogeneous volume filling phase of the, some homogeneous volume filling magnetic field, assuming to dominate the emission and have equal energy density of cosmic ray protons and magnetic field strengths, which is motivated by local ISM observations. However, the ISM and the, slides are out of order. But yes, the ISM and inner disk halo interface or inner CGM are not homogeneous. And so when we actually do the full forward modeling with resolved spectra of cosmic ray electrons and protons with our simulations and make these pretty pictures, we can then directly compare these sets of assumptions to realistic models. What we see is that this traditional set of assumptions would overestimate the magnetic field strength in the 1 to 2 kiloparsecs-ish above the disk plane because this emission is actually substantially dominated by denser, more heavily magnetized gas in the inner disk plane. And so I won't go through the details of this model, but basically we work out a extended equipartition model that relaxes some of these assumptions so we can get a better handle of what the magnetic field and cosmic rays are doing in different phases of the ISM and disk halo interface. But perhaps what's more interesting is the implications of expanding the observable parameter space from our simulations to cosmic ray transport. And so there are two big major schools of thought in what drives the scattering processes of cosmic rays throughout the ISM and the CGM. These are so-called extrinsic turbulence and self-confinement theories. In extrinsic turbulence theories, there's assumed to be some homogeneous isotropic cascade of magnetic fluctuations on which these cosmic rays scatter at their gyroresonant scale, which again is 0.1 to 1 AU for the GeV protons that we care about the dynamics for. And then there's so-called self-confinement theories where the cosmic rays are exciting gyroresonant alphane waves themselves as they stream super alphanically. And so the characteristic scalings for the diffusion coefficient depend on a very different set of plasma properties. And specifically in these self-confinement models, the scattering rate is proportional to the energy density, and so the diffusion is inversely proportional to the energy density of cosmic rays. This leads to very interesting behavior. And so what we see from similar simulations when we forward model the synchrotron emission coming from simulations that have cosmic ray transport that's varying based on local plasma properties rather than constant in space and time is that they predict very different synchrotron emission. Specifically, these self-confinement motivated models, they predict very bright and smooth synchrotron emission that's not like what we see for star-forming Milky Way-like spiral galaxies. And so it adds to a recently growing body of literature suggesting that we can probably rule out this class of models. But really, we have no idea what's going on with cosmic ray transport. And so the model space is basically wide open. And so the hope is that we can continue to use synchrotron emission in addition to all these other observables to try and constrain cosmic ray transport and feedback in galaxies like our own. And so this is basically the summary of what I talked about today, and I'll open it up for questions. Thanks.
Thank you. Very interesting talk. Thank you very much. I wonder, because you mentioned about the different magnetic field and turbulent topology in the halo, I mean, our recent work has observed that the Milky Way has like magnetic ridges stemming from the star-forming ring all the way coming into the halo, very anisotropic. Like, would an anisotropic magnetic field going from the disk into the halo influence the current modeling of your cosmic ray, like you presented in the previous slide?
Yeah, so you're asking essentially if the structure of the field could change?
Yeah, like very anisotropic magnetic field in halo.
Yeah, so it could. So it depends on whether streaming along the field lines is dominating compared to, or streaming or advection along the field lines is dominating compared to diffusion or scattering. So if there's some like coherent outflow that's preferentially moving along the field lines and it's faster than the local scattering rate, or faster than the local diffusion rate that's set by the scattering processes that we don't understand, then it could certainly be important.
This will be our observation result. I will present on Friday. Thank you very much.
One question.
Yep.
Great talk. On the last slide, they showed the differences in synchrotron. Does the gas density also show like similar differences?
Yeah, so I gloss over a lot of the details here, but it's a short paper. So in these simulations, we don't actually evolve the full spectra. But what I'm doing here is taking what we know the local ISM spectrum is and say, well, if these Milky Way-like galaxies have Milky Way-like spectra, and then we evolve them with the full cosmic ray hydrodynamics, what would we get? And so in these self-confinement runs, what ends up happening is because of the inverse scaling of the diffusion coefficient with cosmic ray energy density, you can get local trappings of energy, cosmic ray energy, that then launch these wind that basically blow the galaxy up. And so the changes in the synchrotron are mapping to changes in the morphology and gas density. So this galaxy is basically dominated by a very diffuse, cold for CGM but hot for ISM phase that's dominating the emission, and that's subsequently why it looks like that. So it's because it's really blown out from these cosmic ray driven winds.
Oh, nice talk. You said on one of the very early slides that when you include the cosmic rays, it was actually a very effective regulator of the star formation. So I just wonder if you can go into a bit more detail on that.
Yeah, so since I already showed the movie, I can show another somewhere. Yeah, so essentially what our group, FIRE, but basically a bunch of other simulation groups that have been including cosmic rays have been finding is that if cosmic rays can get into the halo, then they can establish these large-scale pressure gradients that gently accelerate outflows, help accelerate outflows from the disk, and prevent cold gas from falling into the disk and forming new stars. And so what that does is reduces late-time star formation. And so you can see that in this plot of the star formation history. So the star formation rates at late times decrease by a factor of 3 or 4. Subsequently, galaxies basically all move down scaling relations by decreasing their stellar masses by a factor of 3 or 4 as well. And that's also corresponding to a cooler, denser phase structure in the CGM.
Has this only been done for the N12s?
So this has the most pronounced effect at this mass scale, but it's been done for dwarfs all the way up to now AGN, or elliptical galaxies and clusters as well. Kungi has also been working on this.
All right, that's my time again. And all this.